We are given in this case our Young's modulus is 200 gigapascals, which we do need to know for this. I'll express that in pascals. We're given for this beam what its moment of inertia is, 875 times 10 to the 6 millimeters to the fourth, which I want in base units, 875 times 10 to the negative 6 meters to the fourth. And that gap I'll call capital delta is 0.2 millimeters. And we'll need that for our later in the problem. Right off the bat, we have to make an assumption here, like we did when we were looking at those axial problems. Is this a statically indeterminate problem or not? So at B, this is where we're going to make an assumption up front. We are assuming, or we have the option, if we assume that the beam deflects enough that it touches the point at B, which in this case is a rigid body, there's going to be a reaction force at B and A and C. So up front we're saying we're assuming that it closes the gap. We then have to prove that is going to be true within our problem. Because it could, if it did not close the gap, then it doesn't matter if B is there or not because it's not touching it, and that would be a statically determinate problem like we looked at last week. So we saw this when we had those gaps in the problems we saw in the axial type. If we assume it closes the gap, we then have to prove that's going to be true. Again, for these problems, we're probably not going to be solving it if it doesn't close the gap, because then it's just like what we looked at last week. But we have to, again, prove our assumption to be correct. So in our free body diagram, we're making the assumption that it closes the gap at B, and therefore B will have a reaction force. Or we could assume it the other way, assume it does not close the gap, but then we would have to prove that the deflection at B was less than the gap size. So either way, we have to prove our assumption right, or we would be disproving our assumption. If we're assuming that it closes the gap, then we'll have that reaction at B. We'll always have that reaction at A. And across the entire length of this, we have a 30 kilonewton per meter distributed load, uniform distributed load. And we cut just to the left of C, so it does not appear in the internal cut picture. So we have our loads here, our point loads. We'll have a negative AX minus B times X minus 6. Right, so remember, it's positive because it creates a clockwise moment around Q. Right, so that's our EIV double prime. Integrate it 2 times. Right, like in the last problem, we now want to apply our boundary conditions. So in this problem, we have a force reaction at A, we're assuming at B, and at C. So we'll have 3 boundary conditions, and since there are 3 forces, there'll be 3 deflection boundary conditions. So what are the 3 deflection boundary conditions we have in this problem?
B of 0 is equal to B of 12, which is equal to 0.
Right, so at the pin at A, the roller at C, we know the deflections are 0 at both of those locations. And based on the assumption we made at the top, we said that it does close the gap at B. That's why we can see a force at B. So what does that mean our third boundary condition is? Right, negative, because we presume that V positive is going above the horizontal, negative is below the horizontal. So the sign on that is going to be important. So V of 6, we're assuming it closes that gap. So we have a non-zero boundary condition. We're saying that it goes down to 0.2 meters, and then it hits that rigid post, so it can't go down any further. So it makes contact and stops there. So it's exactly 0.2 millimeters below the horizontal. Right, so those are our 3 boundary conditions at A, at B, and at C. Again, they're all deflection in this case. We plug in 0 in our deflection equation. These terms all drop out, and we're left with C2. EI will drop out as well. So once again, we have C2 is equal to 0. Our boundary condition at C, again, equal to 0. When I put 12 into my deflection equation, A over 6, 12 cubed, 5/4, 12 to the 4th, B over 6 times 6 cubed, plus 12 times C1. I can multiply through by EI, and that just cancels out. This equation, that I have A, I have B, I have C1. All right, now the more interesting boundary condition. At B, we know we're saying it goes below the horizontal by 0.2 millimeters and stops there. So we have a non-zero boundary condition. We know that V of 6, we're saying is negative 0.2 times 10 to the negative third. And that's going to be 1 over E times I, which in this case, because they will not cancel out, I do want to include. And this is where it's important. How did we derive our equations? Now these units come into play to make sure that everything is compatible with the way that we're doing it. We were working in kilonewtons, and we were working in meters. So our Young's modulus and our moment of inertia have to match those same units. For the moment of inertia, we're already in meters, so that's okay. We can use that as is. So that's just 875 times 10 to the negative 6. But our Young's modulus is in newtons per meter squared. That's what a Pascal is. However, our equations were derived with kilonewtons as our force unit. So right now they don't match. I can't just put 200 times 10 to the 9th in, because they'll have something in newtons per meter squared, but everything else is working with a base of kilonewtons. So I need to adjust my Young's modulus so that it's in kilonewtons per meter squared. That way all of my units line up here. Divide by 1,000, so 200 times 10 to the 6 is what I have to use there for my Young's modulus. Now I evaluate what's on the inside here at 6. So this term drops out, and I'm left with 6C1. Right, equation 2, I have A, B, C1. Equation 3, I have A and C1. I have 3 equations for these 3 unknowns for these 2 equations. So now again, I need to go back to my external free body diagram for equations 4 and 5. The last step, and my distributed load goes to 30 times 12 is 360 kilonewtons. Between equation 5, I have A and B. Equation 2, I have A, B, and C1. Equation 3, I have A and C1. Between those 3 equations, I can find A, B, and C1. I get A is 68 kilonewtons. And B is 229 kilonewtons. C1 is negative 144. And then if we put this back into equation 4, we get that C is also 68 kilonewtons. And we could have expected that due to symmetry. And we already knew that C2 was equal to 0. So what is the check here to make sure that our assumption, or does our assumption hold up? And how do we check that or prove that? Remember, at the beginning, we assumed it closed the gap. What did we find that shows that to be true? Right, the force at B is positive, meaning that it's pushing up on the beam. Like we saw in the axial type of problems, if we found that, we made our assumption, did all of the math, and we found out that that wall reaction was pulling, that would disprove our assumption, because here the post can only push on the beam. It can't reach up and pull it down to the 0.2 millimeters. So this B being positive, again, reinforces our assumption that it does close the gap. If we found out that that B value was negative, unfortunately after all of this work, our assumption was false to begin with. There should not have been a force at B at all because it didn't close the gap. It would have required B to pull it down in order to close the gap. So luckily it's positive, so it does prove our assumption true. At this point, we can rewrite and get our deflection equation because we know, I'll just keep it as E and I for right now, but we do know their values. We know A, we know B, and we know C1. But remember, this is in kilonewtons and meters still.